Section F2, measuring. This is a nice problem, a practical problem, measuring the coefficient of static friction. This is a fun experiment to do. You get a book, say, some inclined plane, and you put a penny on there, or a coin of some sort, or any object, for example. I picked the coin. This is a book written by my school's first chancellor, Chancellor Highsmith, the University of North Carolina at Asheville. So what you do is you increase the angle until this starts to budge. And that's basically, that's your maximum case. Remember that your static friction is less than or equal to some mu s, n. So when you max out, it's just going to start sliding. And then what you do is you measure like this height, and you can measure this distance like this, because you have, a triangle there. And then what you can do is, with this measurement, say some angle theta, where it starts to slip, I'm going to show you how you get the coefficient of static friction. So we want to have here a little sketch. So here is the incline, like this. Usually I draw my inclines facing the other way, but let's do this one. You never know when you have a client, how they're going to give you a problem. So here we're going this way, and a little coin on there like that. So that's the sketch. And we're going to, measure. We can call this like a y, and this an x. That's going to be things we measure. And in there is your mu s, going against this cover of this book. A little bit of a slick cover. And we're going to call going down as positive, and we'll call this positive for the other direction. So then we go with our force diagram, the free body diagram, and I'm going to go ahead and keep that slant like that. That's my preference, to do that, so I can draw my mg straight down like this. And a quick way to get the angles right, if this closes down, the angle here is going to close down, so it's got to be that one. So we put some more forces in. This is N, and then this is the friction, static friction, going up that way. If you want to show this angle, you can, and if you want to, once again, mention that this angle is complementary to that one, and this one's complementary to that one, and be formal about, more specific about why the angles are equal. Never hurts to do that. So then we go to the equations. Newton's laws, and we'll go with here the incline first, mg sine theta. Mg sine of theta is the one going downward, and that's going to be subtract the friction force, and that's going to be ma. And since this is the case where it just budges and is about to start moving, we can set the acceleration to 0. It's like it's just about to start to move, right? But it's not moving in that last time that you do the experiment right before, and that's where that angle is going to be the one that's going to give us the answer for the coefficient. So then in this direction, you have n going up minus mg. This would be the cosine of theta, that equals 0. Then you have the auxiliary equation, the friction equation, like this. So I like to use the n into here, and then the friction into there, working from the bottom up. It's my style. So we have then the friction force, mu n, is going to be mu. Here, you could write in these little s's because that's kind of a reminder that's the static case. And this is mg cosine of theta, n is mg cosine theta, put it in there for the n. And then when you go to the first equation, you're going to have mg sine of theta minus the friction force, which is this one here. And that's going to equal 0. Notice here that the mass and the gravitational constant drops out. So this is going to be true on any planet. And then you're going to have here that the sine of theta, which is this thing, then minus, just going to be mu s cosine theta equals 0. And that's going to give you sine of theta equals mu s cosine of theta. And now if you divide by cosine of theta, you get this cute formula that the tangent of theta is mu s. That's a nice formula. In other words, the tangent gets you the coefficient of static friction at the point where the coin just budges, starts to move. But the tangent here is the opposite side divided by the adjacent side. So that's nice because that tangent we can measure in the lab, see y over x. And for the case here, now you want to have a lab partner. I put that ruler facing the wrong way. The numbers are backwards. But this is very close. You can read it here in the book. It's a little bit easier to read. This is 6 centimeters. And in the book, it's a little bit easier to read this value here. This one's about 23 centimeters, going this way. With a lab partner, you do a better job. So that means you have 23 is the long one, that's the x, 23, and 6 is the rise, so rise like over the run. And then when you do that, you get 0.26, and don't even need the angle. I mean, that's the answer. Like that's what the answer is. So we have it. That's mu sub s, 0.26. Now, if you want the angle, that's easy to get. That's the arctangent of 6 over 23. And that comes out to be 14.6 degrees. I'll go with 2 significant figures, 15 degrees. Nice. Notice that when you do this experiment, if you put the coin in different places, you may get slightly different results. There's, imperfection, there's not a perfectly smooth surface. There's little differences here and there. So you might do several and take an average to get an estimate of coin on UNC Asheville book cover.